Vamos a presentar todo en inglés a partir de ahora. Entonces espero que no tenga problema. Va a ser una buena práctica para los estudiantes. So welcome again. And it's a very, very special pleasure for me to have this morning Dag, as we call him, Dag Hanstorp, Professor Hanstorp, in a more formal setting. That for those of you that do not know, and that means you have been hidden under a rock. Dag was awarded the Honoris Causa doctorate by the National University of Mexico, which is the highest honor we award as a community. So that was a great privilege, and it was in the screens in the institute. That's why I mean that it would have been rare for you not to see it. So it's a great privilege to have you here in those terms, and also as a colleague and a dear friend. At this point, I would be obliged to talk about the academic, background and achievements, which in the case of Dag are far too many, hundreds of, tens of papers, citations, students and projects, which is the common metric. But I think that the most important metric, and I think I'm not alone in saying that, is that what distinguishes Dag is his unbound and generous capability, and I would say vocation to share not just knowledge but passion for physics. So isn't that quality, Doug, that I welcome you to this auditorium. It's a great privilege to have you here. And it will be a delight to hear you on this mysterious title you have chosen for your talk. So welcome again, Doug, and
thank you.
the auditorium is all yours. Thank you very much.
Okay, so the title of my talk is Physics Across the Atlantic. And just to reflect that I've, over more than 10 years now, I collaborated within Sweden and Mexico. And just to put ours in perspective here, where I'm come from, so here we have Mexico. If you jump on a raft in the Gulf of Mexico and you go out, you have 1/4 chance to end up in my hometown in Gothenburg. It will take some time. And this is the hometown. Gothenburg is in Sweden. It's the second biggest city. It's like the industrial heart. So this is when you come into the harbor. Here you can see the big harbor. It's the host of, but most famously here is the Volvo factory. That's how it's founded. But it's very much an industrial place. And it also has a very nice archipelago outside in the outskirts of the city. And as I said, I'm from Sweden. It's a small country. Population is 10 million, so half the size of Mexico City. The area is about a quarter of Mexico, so we have plenty of space. And if you look on this map now, green means forest. So basically, the whole country is covered with forests, and so basically, the forest industry and paper industry is a very big thing. Up in the mountains, we have the Arctic when we have the mountains where there's any vegetation, and a few spots here, which is basically the land base after the ice that has risen up, is very good farming land. And the climate, I mean, we're very high up, 57th degree, so it's Arctic. In principle, if you look on the globe, but due to the Gulf Stream, thanks to you, we actually can live there because the temperature is not, it's cold, but not Arctic climate. And what I've been doing is what I think, I'm very honored to get this degree, Dr. Causa, but I think it's for my work in the collaboration I'm most proud of. And it has been in the framework of what's called the Linus Palme exchange program. And just to say, Linnaeus was a botanist in the 1700s, and he basically systematized botany. So gave all plants, all animals two names. That was his origin. So he was like a precursor of Darwin, who then could see the pattern of the evolution. And he was a professor in Uppsala. He thought very much about himself. He called his students his disciples. So only Jesus and Linnaeus called his students disciples. And he sent out his disciples all over the globe to explore and investigate, and then bring back the knowledge. Olof Palme is maybe the most famous politician in Sweden. He was a social democrat in this prime minister in the 60s, 70s, and 80s. And he had his heart for the global perspective. So he visited many, many different countries. Actually, in 1984, he came to Mexico. And he had, as I said, he had a lot of contacts with countries over the globe, and he brought a lot of those, in particular, students back to Sweden to be trained. And unfortunately, he was assassinated in 1986 on the street in Stockholm. And then this Linnaeus Palme program by the Swedish government, basically the idea was that we send out students and we bring in students. So basically the outgoing students, the students that have come here to UNAM is the Linnaeus students, and the Palme students are the one coming to Sweden. And this has been ongoing since 2014, and it all started by me doing research at ALS in Berkeley. And then at Berkeley, there was a beamline scientist, Alex Aguilar. He was responsible, and he's an alumni from UNAM, and we started to collaborate. And we had a good idea. We said we needed some funding. And then I found this Linnaeus Palme program. But they didn't allow exchange between Sweden and the US. But then I said, I have a colleague in Mexico, Antonio. And said, so then we started the collaboration, Gothenburg, UNAM, with the aim to develop a new tool at ALS. But then for political reasons in the US, that was closed down. And Alex went to industry. But we had already started, so we then continued the collaboration. Then later, Professor Remigio took over the responsibility for this, and we have keep going since then. Unfortunately, the very Linnaeus Palme program was closed in 2022 by the Swedish government due to the situation in Ukraine, because the Swedish government really wanted to focus all their money going out to support Ukraine. Very unfortunate for us, but we have other means with Erasmus Plus program, so we can continue. And during those years, we have had 5 teachers from UNAM and 11 teachers from Sweden to come in exchange programs, all funded by this program. And we have had in total 36 students in the exchange program. And the typical thing is a student coming from 1-year master studies doing the master thesis. And 25 UNAM students have visited Sweden, and 11 Swedish students have visited UNAM. And also to be in a subject like physics, it's kind of amazing that we managed to have 18 female and 18 male students in the program. And now this is my projection of the world. Highlight the important things. Is this not the Mercator projection? And so, just to show you here, each dot here represents one of the current location of the student that has been in the program. And the black dots are the Mexican students, and the blue dots are the Swedish students. And just to highlight that behind each dot here is a very important step in their lives. And just to mention one, Israel Boledo, he is now working as a researcher at the Research Institute in Sweden. And you can just read his statement he gave when I collected all the information about this. And of course, for each dot, I could make the same kind of story. Second one I can show you is Amelia Telanderson. She went to study here as a sonographer. And then now she's back and doing a PhD in the Gulf of California. And just to show you that I said it's Arctic. Well, this is one day when we came and we had a lot of students coming up. This is Ademir, also from UNAM. We had a big snowfall, so I went home and took all my kids' stuff out. So we went down to play in the snow, which was many of them for the first time for these. So, yeah. It is, yes, that's right. So with that, that was kind of the introduction to why I'm here. And now I would like to just tell a little bit about my research interest. And basically, I can say I have 4 different main topics of interest. My main research is atomic physics, where I study negative ions. And that I will talk about later. But I also have a lot of other projects, which I've been spending quite a lot of time on. One is what's called optical levitation. And I will just show you a video here. What you see here, this is like 2 centimeters. There's a 1 watt laser beam in this direction. From above, we spray bicycle lubrication oil. The oil falls down, and you can see scattering when the oil drops hit the laser beam. I mean, it's basically filled with oil all over. And if we continue a little bit further, there, maybe you could take out that light, but it's fine here. What you see here now, 1 oil drop falls down, hit the laser beam. The laser light is reflected on the droplet, and since each photon carries momentum, if it's sufficient intensity, you can balance gravity, and you can hold this drop as long as you want. Which is, of course, a very nice tool to do a lot of different experiments. And I will later in the talk present one of the experiments we've done with this optical levitation. I mean, this technique was awarded, Arthur Ashkin was awarded the Nobel Prize. And if you're in biology, he also invented the optical tweezer, doing the same thing in the microscope, where you can manipulate cells. Second thing is that I do like applications of femtosecond spectroscopy, simply because for the atomic physics, we have a femtosecond laser, and there's many different applications. This one, what I show you, is a collaboration with an Indian group, and that is about combustion. So, as we say, Volvo is the hometown is in Gothenburg. The diesel engine has been improved to perfection. You have a very good efficiency, and the key to make an engine working is that you atomize. You spray in the fuel, and you should atomize it to as small droplets as possible to maximize the surface so you get a good combustion. When you change to biofuels, the structure of the biofuels are different. So that means that you don't have the same efficiency biofuels, although you have the same energy in the fuel. So that is a hot topic now to improve combustion engines. And we just started, since I'm an atomic physicist, we start from the bottom up. We take one droplet, and this droplet here is trapped in an acoustic trap. It's about 1 millimeter in size. And then we focus in the center here a femtosecond beam. So we vaporize the droplet in the center. And I can just show you what then happens. So you can see how the vapor in the center expands and expands. And this is recorded with high-speed cameras that can take 600,000 pictures per second. And of course, in this case, you want this, when they break up, to go into as small pieces as possible to maximize the surface in the combustion. So my final research interest is physics education research. I have a background as a teacher, and we have done a lot of things, how we can develop physics, how we can develop experiments to improve teaching in physics. And what I will show you here is an experiment I was asked to do during the COVID, because as everywhere, all the students were sitting in the dormitories, meeting nobody. And I was asked by head of studies, can you make anything that our first year students can, so they can come out and see something and meet something? We couldn't put them in the lab because that was out of the restrictions. So after some thoughts, I rented a football field, I bought a drone, and I will now show you what happened here, and you can think, which is the physics. This is a classical undergraduate physics experiment, and think about it and guess what it's showing. I don't know how to get rid of that. Well, what it is happening here is that those two things there is loudspeakers sending out a 440 hertz single frequency sound. And I asked the student, please close your eyes, walk around, and stop where you hear the maximum amplitude of the sound. So basically, this is a physical demonstration of the interference of sound waves. And here you can see that how they align the different maxima. I'm a little bit ashamed of my instructions here because I'm an experimentalist, and I said to the students, please find the maximum intensity. I should have, of course, asked them to find the minimum, because from an experimental point of view, it's much easier to find the minimum because that's the point where the sound disappears. So you hear it's more difference if you go from 0 to 10% than you're going from 100 to 90%. Later, this was, we have a science festival in Gothenburg. So actually, I redid this experiment at the big football stadium that seats 50,000 people. We had 400 kids on the ground and doing exactly the same thing. It worked nicely, except that there's bigger noise if you have 11-year-old kids being the samples of the loudspeakers here. Okay, with that, I just want to go into the main field, which is negative ions. And let's see, and the question you can ask then is, are negative ions good for you? Which was asked in the New Scientist in 1973. And I will see if this works now.
There's a very interesting way you could boost your mood and actually become healthier through negative ions. You ever wonder why you feel better when you're next to a huge waterfall or you walk into a forest crashing into the rock? And there's a common denominator with all those items I just talked about, and that would be negative ions. There are a lot more negative ions going on.
So this is just Googled on negative ions. You can see, if you look here, everything improved in life if you're just exposed to negative ions. So of course, that's a very good motivation for me to do research in this field. But coming to the atomic physics side, the reason I study negative ions is that, okay, if you take an atom, then you have the Coulomb attraction pulling the electrons in. But if you have an atom and want to make a negative ions, you have to have this kind of symbolize an atom. And if I have now an electron here, there's no long-range force. It doesn't want to be bound. So the question is, why do they exist? But the reason is that when the electron is approaching all the other electrons are pushed on the other side, and then you induce a dipole, and this dipole counteracts and binds. And that basically means that if you, for an atom, you would have a 1/r potential in the long range, but here you use that the induced dipole moment get r to the 4 power. This gives negative ions very special properties. And if I just show you here the energy level diagram, then the atom, you have the ground state, a lot of excited states in the Rydberg series, and it's about 10 eV. For the negative ions, you typically only have one state, and the binding is about half an eV typically. And what's interesting here is that the potential, the model potential that you can describe the basic properties of negative ions is basically the square well potential with finite height, like the third lecture in quantum physics introductory class. So it's a good model system, but it's extremely complicated to do the accurate calculations. So then why we study them? Well, as I said, it's good for benchmarking. It's a model system, and they appear in many applications, like in astrophysics. And now I just will pick one of, I've done a lot of experiments on different elements and for different reasons. I will show you 2 or 3 examples depending on my timing here. The first one is a study of astatine. That's an element in the periodic table. You maybe not have heard about it, but because it's the least abundant element on Earth, there is 70 milligrams in the crust of the Earth, not per something, per crust of the Earth. And if you go to the periodic table, it's down here. So it's the heaviest halogene. It decays, so it's not stable through alpha, but it is used in medical research, and it's used in something called targeted alpha therapy. And the reason is that the lifetime and the energy of this is very good, and also the daughter is non-toxic and non-radioactive. So what people do is that they take astatine radioactive atom, put on an antibody, inject in the patient, and this antibody diffuse around. The lifetime is 12 hours. So hopefully within 12 hours, the antibody is attached to a cancer cell, and then it decays and can, with high probability, kill the cell. So you can target the, instead of getting that big dose of radiation. But nothing is known about its chemical properties. And as I said, the affinity is the binding energy of the negative ion. And if you look here, this is a plot of the electron affinity of the halogens. So you have fluorine, chlorine, bromine, iodine. And when we started this project, these were the predictions of the astatine. There's a wide range. I mean, it was not known at all. And we set up to measure this. And now, as I said, we couldn't dig it up from the ground because there's too little of them. So we went to CERN, where we can produce radioactive isotopes. And this is the accelerator complex of CERN that you all have heard about. I mean, the big accelerator LHC, where they found the Higgs boson. You start out here with H-. You go to the booster, and then you go in the different accelerators to increase the energy. But from the booster, we can take out the beam of the protons in GeV range and go into a facility that is called Isolde. And in Isolde, we take the GeV proton beam and smash it into uranium. We basically have a tube of uranium, and then the protons goes in. We don't get a chain reaction, but we smash the uranium in all possible pieces. So we basically produce the whole nuclear structure. Any element with any mass we can produce. And then we have this tube, it's about this size, and then we heat it to 2000 Celsius, then all the atoms diffuse out. You go into an ion source, you ionize, you make a beam out of them, and then you mass select, and then we can get the specific astatine isotope out of this ion source. And this is the hole with a lot of beam lines where you then come up and put your own experiment. And for that, to do this, it took quite a few years. We built this detector called Gandalf, and it's a very simple, actually we named the name because I wanted to claim that it was our, so I told my students, make an acronym where Gothenburg is in the acronym. But it's a very, schematic is very simple. We have made a beam of what we want to study. We take the beam here, we deflect it, and then we put a laser beam on top of it, and then what can happen here is that if the astatine negative ion, if the photon energy is large enough, we knock out the electron. If it's too small, nothing happens. Which means that after here, we can have a deflector bend out the astatine minus and have the atom that we have produced by what's called a photon attachment, knocking out the electron. Then we have good lasers, so we can just tune the photon frequency and look for what energy do you need to release the electron. And the astatine atoms impinges on a glass plate produce electrons that we can detect. And after a lot of work, well, as I say also, this is extremely challenging experiment because the density in here of astatine minus is 0.01. So when we, for 100 laser shots, in one of them we have one astatine minus in the interaction region. And since we produce neutrals, the light that we use is hitting the same detector. And the light pulses we use have typically 10 to the 14 photons, which means that we have to see one atom striking the plate, whereas 10 to the 14 photons must pass out without extracting the electrons. That takes a lot of work to get that to work. And here you can see a picture of this detector, and this is what we came up with. So this is basically we scan the photon frequency and measure the rate of astatine minus produced. And at this point, we see an onset. And this is a well-known fact that there's a square a function called the Wigner function, which can fit and get out the position of this that corresponds to the electron affinity. And we did this in experiment, and this is the final results we got. A group of Anastasia Borskevsky made the theoretical calculation. They're extremely good. We had worked for years, and we had this two results ready at the same time. And then my student and her postdoc was invited to a conference, and we decided they cannot know each other's numbers. So they were talking back to back. My student came up and showed this number, and the talk after the theoretician showed this theoretical value. And that was just to be confident that we don't have bias in how we evaluate these ones. So that was published in 2020. Sebastian Rothe at CERN made the same study on astatine on the neutral to determine the ionization potential. And if you know the ionization potential and electron affinity, then you can calculate what's called the electronegativity, which is actually is a key number in chemistry. Because if you take two atoms and put them together, they will form a bond. The question is, will it be a covalent bond or an ionic bond? If they have the same electronegativity, it will be a covalent bond. If they are very different in electronegativity, it will be an ionic bond. And so that's by getting out this number, the chemists who produced this astatine on the biomolecules now have the key number in the chemistry behavior of astatine. Okay, and these are the people who have actually been doing the work. Is David Leimbach, Julia Karls, and Annie Moval. With that, I will change gear and go to the next reason to study negative ions, namely that they're good model systems. And I know Antonio was just teaching the introduction to quantum physics, so I saw, and of course, when you start with to learn about the atom, you learn about the wave functions, and then you teach the students that you will describe it by the radial and the angular distributions. So you say that you have the differences showing the angular distribution, and these are the radial distributions of a typical hydrogen atom. So here you have the S wave, and this is the P wave. Now, this, of course, we tell them, but the student don't see this. They just have to listen and accept and trust me that this is correct. But now, if we do this photon attachment, a photon comes in, knocks out an electron. The outgoing electron will have one of those angular distributions. So if I take a p electron like an astatine, then the electron will go out due to selection rules as an s electron, so it will go out as a spherical wave. But this one will not be spatial. Instead, it will be a function of the electron that it goes out and expands in time. So you do that, you will get a wave function that expands and expands until it is detected. And what we do then is use a technique that is called VMI. So think about it, you have your ion beam here, you have the laser beam coming in, and you produce this wave, the quantum wave. Then you take an electric field and you just push this sphere because it's charged. So we can push it into a detector. And then you basically will measure the two-dimensional distribution of a three-dimensional wave. And here you can see the setup. So basically we have the laser beam, the ion beam. Here we have the fluorescent screen and a camera to observe this. And if the energy is zero, it will just go out perpendicular. If it has some energy, it will go out and produce a circle. So we did this on silver minus. And then we took a photon that was too little energy to photon attach, but with multi-photon processes, with two photons, we can get out the electron, and then you can do what's called excess photon detachment. If it's intense enough, you can have it to absorb more photons than needed. And this is what we then see. So here, that means that this is the energy corresponding to the overshoot here. And then the next one means that you have absorbed 2, 3, and 4 photons. And silver has an s electron, so it's a p wave. And think about the p wave orbital and smash that into a plane, you get those bows. We did this, and the student who did this, Mikael Eklund, he had a background in mathematics. And he said, it's a pity that we don't see the three-dimensional structures. But why not use tomography? So then we did the following. That we took the same setup, but then we took the laser beam, and instead of having it fixed in one frequency, we took pictures for every angle. And what you will see here, if you now look at the angle, this is the what we have projected on, and here you can see what we see as a function of angle. And I'm only an experimentalist, but if you now take those stack of images and you do exactly the same thing as they do at the hospital, at the CAT scans, you can reproduce the full three-dimensional, so this three-dimensional picture, which you see here. So now I can actually show the real wave function in 3 dimensions projected here, which I think is very nice. This was, of course, all expected. But as to visualize science and the part of my interest in teaching physics, I think this is very valuable. Okay, that was how we can use the model system. Now I will go to applications. And I guess this is basics for you, but just to remind about the carbon-14 dating method. Cosmic ray hits nitrogen in the upper atmosphere, produces carbon-14. That is mixed over, it takes many years to mix around, but in the end we get this is the upper process, then you get a ratio about 10 to the minus 13 of carbon-14 versus carbon-12. And then carbon-14 will decay back to nitrogen, and the half-life is 5,700 years. And this is, of course, done to date biological materials. If you have an excavation, you pick up a bone or something, you can measure the rate of carbon-14, the density, and then you can say this must be 8,000 years old, which has been a tremendous success in archaeology. And this was, Libby was awarded Nobel Prize in '62 for finding out this method. To say now how you do these experiments. I brought something here. I don't know if you can guess what it is, but this is 1 mole. It's 12 grams of coal containing 6 times 10 to the 23 coal atoms. And that's actually the definition of the mole is actually the carbon. So now, if this is dependent if it was an excavation or a modern, I can now measure the carbon-14 level and get how old it is. But this is question, it's quite a few carbon-14 atoms in here. So I say, can you find a needle in a haystack? Well, I just Google, a hay bale is 300 kilos. A haystack I estimate to be 30 hay bales, that's 10,000 kilos. A needle is 1 gram, okay? That means that to find a needle in a haystack is 1 part in 10 to the minus 7. Okay, but now we're talking about 1 part in 10 to the minus 13. So it's a question of finding one needle in 1 million haystacks. Unless it's old, because then it might be 10 million haystacks. Okay, so it's very few of them. And what they found in 1977 was that, because basically Libby, who invented this, he took this piece of carbon, he took a Geiger meter, put it up front, and wait for the decay. But that, of course, is not too many of them will decay, because it will take 5,000 years for half of them to decay. So if we now like make a back of the envelope calculation, how many will decay? I want to measure, I can accept that I wait for 1 hour to measure the rate of carbon in that one. So we have 12 grams of carbon. The fraction of carbon is 10 to the minus 13. Assume it's 11,000 years old, then it's only 25% left. You get a decay rate, and in 1 hour, 300 of them will decay. But of course, if I put my Geiger meter here, only a few fractions will go in that direction. So I maybe get a few in 1 hour. And actually, I have to destroy the sample to measure. Now, if you instead make an ion beam, then we'll make the same calculations. And I can say, that should be micro. You can typically make 100 microamp beam in an accelerator. That's kind of intense beam. So assume that I put that sample in an ion source, make a beam. But that means that I make 6 times 10 to the 14 atoms, carbon atoms per second. And that means that I basically produce 15 carbon-14 per second, which means that I only need 20 seconds to get the same amount. And the question, how much sample have I produced then? Well, then if I do that calculation, I need 2 times 10 to the minus 3 mole, corresponding to 0.24 milligram. So I need a grain of the carbon to put in my ion source, measure, and then make a beam and select and measure the number of carbon-14 atoms. So now you can take a string from a painting if you want to date it. But so we want to detect carbon-14 minus. The problem now is that with a mass spectrometer, there could be other things that has mass 14. It's called atomic interferences and molecular. Carbon-14 could be, you could have nitrogen-14. But if you start with a negative ion beam, you'd get rid of that, because that one, this potential is too shallow, so that cannot form a negative ion. Pure luck, because there's only 10 elements that cannot form negative ions. If you take molecular interferences, well, what do we do with them? I mean, you can have carbon-12 H2 minus. Well, what you do then is that you take your sample, and out of your source, you get rid of the atoms, you bend, you accelerate to MEV in a tandem accelerator, you pass your beam through foil, and if you pass a beam through foil, it just explodes, and on the other side, you have all separated, and then you get a beam of H, C, and C12, C13, and C14. You can take this out and detect it. This has been developed into perfection, and of course, there's many famous samples when they tested this. Now, just say, this is one of them, the most famous radiochrono isotope, but there's a lot of them, and I will just briefly say that this one is very interesting for other reasons, not to date the time of age, but if you have this chlorine-36 is produced if calcium is hit by cosmic radiation, and it has a lifetime of 300,000 years, which basically means that if you have a glacier that retracts, then calcium out here has been exposed for maybe 20 years. Here they have just been started to be exposed. And if you now can measure the chlorine-36 content, you can measure and date the glacier retraction by picking stones. But here you have a problem that this one decays to sulfur-36, which is stable and existing. So, and this can easily be produced to a negative ion. So how do you do? Well, the good thing here is that sulfur has a smaller binding energy than chlorine. So we can use the same technique that we have done. So I was contacted by the group in Vera in Vienna, who is the leading group of this, and say, can we do something? And basically what we do is that we take our negative ion source, we pass it through a very intense laser beam, and then we can get rid of the background and only pass out the what we want to see. And that meant that we basically made an extension of this machine. And just to show you here, if we now pass the beam of chlorine chlorine and other things, the red shows what you had before we passed the laser beam, and the blue shows was after. And it's only the chlorine that survives passing this laser beam. So now we have a tool to detect all the other isotopes. And with that was kind of an application. And I think now I've showed you that we have various reasons to study negative ions. Last 5 minutes, I will go back to optical levitation. And you saw already we trapped the droplet. The droplet, if you spray out, it gets charged. So if you trap it and apply electric field, the droplet will be pushed up in the electric field. And then we can take a lens and on the side basically image this. And then we take an alpha source and approach. So we have a droplet that it has maybe 1,000 extra electrons. And then we take the alpha source and it will knock out electrons. Then we apply a sinusoidal electric field. And the blue line here shows the electric field. And the green one is the position of the droplets. Now, if you look here, you see how the amplitude goes down because you knock out electrons. And at the same time, you're down and you have no electrons left. But then you start to knock out electrons from the inner part to make it positively charged. And if you look here, you can see that here they are out of phase, the electric field and the particle, because it's negative. Here they are in phase. So we go from about 500 excess electrons to a deficit of 500 electrons. Very nice way to show a lot of physics, basic physics. And I will show you here a video of this. No, I have to go here. And what you see, so here you see the two spots projected on the wall. This is filmed with a cell phone. And here you see a school ruler. And then we added this, and each line here corresponds to 1 electron being removed. And if I click here, you can see that it goes in steps. And you can actually see that one step there is a single step. But the problem in this experiment is that the alpha particle has MeV energy. So each alpha can emit a lot of electrons. But we were happy about this result. But then we proceeded and instead say, if we go to UV laser, then according to the Einstein's Nobel Prize, the photoelectric effect, each photon can only emit 1 electron. And this just 2 weeks ago, my students got this result. This is the position of the droplet when we have replaced the alpha with UV light. And you can clearly see the steps of the electrons. So each step here is simply a single electron that is removed. So this is basically a way to show the quantization of charge. And the two people that have done this is Javier Marmolejo, who is a former student from UNAM, who first took part in the Linus Palmer program, and then he was hired as a PhD with me and defended in May last year. And Oscar Isaacson, who's a high school teacher who come to us to do research on Tuesdays. And with that, I'll say, conclude. There was a lot of collaborations, but still more to come. This picture is from 1.5 years ago. Maria Soledad from UNAM and Alexander Dimitriev from Utah University is signing a memorandum of understanding for future collaborations. And by the way, that is a Swedish king who's checking that everything is done in the right way here. And then at this point, we have 1 scholarship available. So for 1 year, full year scholarship for master studies at Gothenburg in the year 2026 to 2027. That will cover airfare, cost of living, insurance, and there is no tuition fee. And it's open for anybody in the 7th semester or above. So if you are interested, you should get in contact with me or Remy and before the 1st of March 2026. We're still trying to get more scholarships and more programs. And we're also working on a dual degree for PhD students. And that is just after long negotiations between the 2 universities, this is about to be signed. So we hope that will happen soon. Sorry? By Christmas. Good. Yeah, Christmas present. And if you're interested in any future collaboration, feel free to contact because we continuously working on finding new funding possibilities. So contact me or Remigio, or come here afterwards. And with that, I should say, this is not my work, but these are the key people. This is my PhD students that have done the work been involved in the last years. And these are the people who have paid for what we do. And this is Moa Christiansson. She also helped me to do a lot of the slides. And this is the next generation of students now working in the group. And with that, I thank you for your attention.
Thank you very much, Dag. That's very, very interesting to see all the scope of things. I haven't seen the isotope part,
no,
so I'm discovering new things, and this ICE was fascinating. Mm-hmm. But now we're open to questions. I would really like to encourage you. There's a lot of students here, so if you guys don't feel confident with English, that's okay. We are among friends. You can ask in Spanish, and then I will translate to.
And I will guess what you asked.
And then he will reply in German. And for your colleagues, you can obviously raise your hands. And this the session for just open and friendly discussion of things, of many of the topics that were covered here. So,
anybody? Yes.
Okay. Eso.
Bueno, primero que nada, muchas gracias por la presentación.
Thanks a lot.
Y a mí me interesaría conocer más un poco de el perfil de las personas que buscan para este programa.
Yep. He's thanking you for the presentation and asking further details about the profile of the students that you take into your group, or for the research or for the exchange program.
Yeah, so we have a deadline, so basically it's like there's a cut for the level you have been, but you should be on the level where you can do your master project. And then everybody is free to apply, and you basically write a personal letter and you send in your transcript or records. And we basically want to have good, talented students and people with curiosity who want to do things. That's the two main things, I would say.
Gracias.
Sí, por si no quedó claro, estudiantes de séptimo grado con un alto grado de curiosidad y típicamente eso no lo dijo Dag, pero lo pone Remy, selecciona estudiantes de muy buen promedio y de muy buen performance académico.
Ajá, para completar la respuesta, o sea, que ya hayas llevado electro y mecánica cuántica, porque es el tema que trabaja. Que ya tengas el 70% de créditos, porque la idea es de que no pierdas el año que se vaya a estar allá, sino que cuando regreses te gradúes en tiempo y forma. Y la solicitud que van a ver el email es: necesito tu historial académico, tu currículum vitae y una carta de motivos para ver, y todo en inglés. Tienes que ser proficiente en inglés porque si no, no. ¿Sí? El anuncio ya está circulando, chequen las redes del ICF y la fecha límite es el 1 de marzo para esta posición. Cada año hay más. We have another question.
Good afternoon, Doctor. And it was an excellent talk, and I congratulate you for your Doctor Honoris Causa. Just a small doubt, maybe. I mean, in one of your slides, you showed that there is a deflection of ions from a graphene-layered quartz.
Yes.
I mean, what exactly is the role of graphene? I mean, in this case.
Okay, that took a lot of work and many years.
Yeah, that caught on my attention.
You have the light has to go through. So basically, you want a proper material that is completely transparent and conducting. And if you do your solid state, you know that that's kind of contradiction.
Yeah.
Because if you want it transparent, you take a glass that is isolating, or you take a metal that is conducting.
Yeah.
So we need it, but first of all, the light has to go through because we cannot have the light stay in the chamber.
Mm-hmm.
And it turned out that so we started out with just normal glass and ITO, tin doped indium oxide, which is used in liquid crystals. And that's fine because then you can pass visible light through.
Right.
But when you come down in the UV, then that layer starts to emit electrons. And then, of course, we get a huge background. Quartz is transparent all the way into UV, and a single layer of graphene simply is not really not absorbing any light. And so the reason is that the graphene is just to say you shoot the particle through, one electron from graphene is knocked out, 1 or 2, and we detect those. And then by the conduction of the graphene, you can replace them. Because you can put a quartz plate there directly, but then after 10 or 100 emitted electrons, you will build up a potential, so then electrons will just be pulled back in.
Right. So graphene is basically acting as a source of electron there.
Exactly. That's the only thing it's doing, but it's doing it in a perfect way.
Okay.
Yeah.
So I mean, the question, the perennial question that is with graphene is whether it's a semiconductor or a conductor, because while we are doing experiments in our lab, we are having, doing experiments like Morse Schottky and all, and it is giving a conduction band, but it is behaving like a semiconductor, but actually it's a conductor. So, I mean, is there really an answer, Dag, for this question, what it is exactly?
Well, then I will have to consult a solid state person describing what's happening in graphene. But I know we also have the problem that, which I didn't show here, but many experiments we do when everything is cooled down to 13 Kelvin.
Right.
And then we cannot use semiconductors.
Yeah.
Because then they will be insulators.
Well.
Yeah. So from our point of view, we tried many materials.
Right.
And when we tried graphene, it worked. We have never tried anything else.
Right.
Yeah.
Okay.
That's the simple. For us, it's only a tool, and not it's not our study, but it's our tool we need for the detection.
Thank you very much, Dag.
Very good question.
And congratulations once again.
Thank you.
By the way, Thomas Stegman works on this conduction problem for graphene, so you may just cross a few meters away from you. There's an expert.
Yeah.
But that's a theoretician.
Oh, yeah. Sorry.
My question is about the figure that you showed for the experimental information on the wave function.
Yes.
So negative ions have particularities. You showed, for example, the electronic correlation.
Yes.
And from that figure, can you see something specific of negative ions, some characteristic of that distribution?
So from the figure, you basically only see that it's an s electron. And what happened is that if you take hydrogen and take an s electron, you really have that is good quantum numbers. The 1s describes the wave function of the hydrogen. For negative ions, actually, this electron correlation, you cannot describe it as then silver is like 4s squared, is the valence electrons. But actually, if you look and do the calculations, you will find that it's really 4s squared plus with a factor plus 5s squared plus 4s plus, and a long series of components to describe it. So to measure the absolute value of this, you really have the electron correlation. But all those states that build up this wave function are S waves. So that means that they give the same picture on the screen. So I think that experiment is good to demonstrate the wave properties of electrons in the system, but it doesn't help to get the qualitative numbers. Then you have to measure the affinity and do the exact calculations of how tightly it's bound. Because that is the whole point with this, so I would say this is the proton and you have two electrons, and in order to bind, they have to be on opposite side, so they have to correlate. And the more they keep on opposite side, the closer they can come and the more tightly bound they are. So if we measure the binding energy, it's really a measure of how much electron correlation we have. And that's why it's a probe to measure, to test theories. Do they include electron correlation in a good way? If they can predict negative ions, they are very good. And if you don't include negative ions, H minus does not even exist. But we know that it exists, and it's very important in the solar atmosphere.
I have asked the same question about correlation to Remy, and this is the first time I actually understand it. Thank you.
Yeah, he's much a better teacher than I am.
Yeah, absolutely. Absolutely, yes.
Any more questions?
Students, feel
No?
free.
Then let me ask this tricky question to Professor Hanstorp. First, of course, congratulations for the honorary doctor. Now
Thank you.
it's his second honorary doctor, so we need to call him a square professor. But the question I want to make, could you tell us, and particularly because our two guests that are exactly at the front of the auditorium, you're also working on applications in medical physics with the bone cutting
Yes.
applications. Can you tell us a little bit what is the idea about? And also Gerson is here. I think if he gets lucky, he will be your next postdoc.
Okay. So, I mean, you saw the picture where we took the femtosecond laser. I mean, that's when they got, a few years ago, they got a Nobel Prize for this, the developing of the femtosecond laser. And the whole point is that if you take a laser pulse and you push it together, make it shorter and shorter, and you get more and more intense beam. But you don't increase the total energy. So in medicine, they started to use lasers to cut. But if you took a standard laser and cut, you basically burn and destroy all the cells. But if you take a femtosecond laser on living material, you basically break bonds, and you can make a cut without heating the material. So I was contacted by a medical doctor. He Googled lasers Sweden and found me and said he wanted to cut mice bones because he's studying leukemia. And then he wanted to see, so I mean, leukemia is the blood cancer, and those cells are made in the bone marrow. And he wanted to get the bone marrow out, but keep the spatial distribution. But normally, if you crush it, he had done before, they crush the bone, get the bone marrow out as a soup of bone marrow. But he wanted to keep the spatial resolution. So he came to us, and we just had the bone, and we take a femtosecond laser beam, and we just moved it through the bone, and we could cut it. And then he took the bone with the surface of cells, went home, and could cultivate and see that all the cells on the surface was alive. And that we're now working on, because next he wants to slice up the bone, so he can then put on slides and make pictures of each section, and then build up the 3D structure of the bone marrow of healthy and mice that have leukemia. So it's kind of the same as I showed you with the oil droplets. We have the tool, and we work with different people.
Good, thank you. Yeah, it's expanding, guys. So if you want to, he has so many projects. He just talked here about the few ones that he's interested in. He's the expert in lasers in Sweden. The chairman is.
Well, okay. We have the Nobel laureate in Sweden, I guess.
Okay, that's
cool. So they got the prize for the Nobel for the laser. So
more questions? No.
Okay. I guess that's the case. You can always, I mean,
after
this talk, you can
walk around here. So
we can help translating if you are not confident with English. Otherwise, just feel free to get close. And just to end formally the session, we would like to thank you very much warmly for your very beautiful talk, Doc. Thanks a lot. Muchas gracias.